Okay, welcome everybody to this IEEE GRSS webinar. Together with me, there is Francesco Mauro and Alessandro Sebastianelli. We are both part of the IEEE GRSS Quest Technical Committee, and today we are going to have our second webinar of the series. We have together with us the Italian company called Thales Alenia Space. They are going to present several works about quantum technology applied to the space sector, to Earth observation also. And just to say a few words about Quest, it's a new technical committee that has been recently created. And we are split in two main groups. One is about quantum sensing, the other one is about quantum computing. And today, I mean, the webinar will be covering probably both of those aspects. And we have many speakers. They're going to introduce themselves before their presentation. And just to conclude, before I let the floor to the speakers, I want to say that the audience is also even bigger today because I'm currently in the University of Pavia, and there are people following you from a course that I gave together with Professor Paolo Gamma and Professor Silvia Ullo on quantum computing for Earth observation. So you cannot see them, but they are here ready to attend your nice presentation and to ask questions through me. So thanks everybody again for joining, and please, I let the floor for the next speaker.
So here I am. Good afternoon. Can you hear me properly, Alessandro?
Yes, we can hear you.
Perfect. So welcome everybody. I'm Tommaso Catuogno. I'm working in Thales Alenia Space Italy since 6 years now, and I'm part of the domain observation and navigation Italy. And since my beginning in TAS, I had the goal of starting this R&D road toward quantum technologies in the domain. And today I will start sharing a brief introduction on what we are doing in Thales Alenia Space, and then we have many speakers with us, dipping into the details of what we are doing as per today. So I'll share my screen. Okay, should be visible. So as I said, I'm Tommaso Catuogno, and what I said is that I'm part of the domain of observation and navigation in Italy. So in Thales Alenia Space, our company is Italian and French company, and we are divided in many domains that are kind of groups, big groups in the company. We are in the domain observation and navigation of Italy, and specifically in Italy, we focus on radio frequency Earth observation, so synthetic aperture radar, or anyway RF-based Earth observation and navigation. So we are a prime contractor of many satellites, many systems like Galileo, EGNOS. We are pushing a lot and working on Moonlight. We are a prime contractor of many of the Sentinel satellites from the European Space Agency, and in general, we work as a large system integrator. So what we do, our customer mainly is the European Space Agency or other agency in general, and we design, manufacture, and supply end-to-end satellite system in many different orbits, many different kind of satellites, and this is our work in general as a company. And these actually lead to our product. So we try most of the time our system change time by time, but we try to have products that are kind of building block that are used and adapted in each mission. And this is our product are very various and distinct. We have radars, payloads. We have also OBC, so onboard computers and system to be run on board, the PDHT. We have satellite structure in different sense. So we have very various system, various type of products. And in this domain, we started the work of quantum computing, quantum technologies exploration 6 years ago, and we started asking ourselves what could quantum technologies brings to such kind of product. And the answer is complex because quantum technologies are kind of very broad um, domain. It's also hard to well define what is the constraint between the kind of technology, classical and non-classical technologies. The main feature are that they are very low TRL in general, but altogether they could bring disruptive advantage to our system. So it's worth investing because the maturity of the technology as per today is still very low, but the potential is enormous, and also the range of applicability on our product is very wide. Altogether, the market is growing. Also, the European Space Agency, the Italian agency, and all their agencies are investing a lot. The number of opportunities and project is growing very quickly. And altogether, there are many contexts in which also other kind of entities are interested, as military or governative entities are interested in these kind of technologies, because there are many sensor, many strategic elements that could be empowered by this kind of technology. This is the reason for which we are investing, and altogether in our vision, let's say for our company, we stick together. Also, if we well know that there are different things, also the optical and photonic technologies that we started to study altogether with the quantum technology ones. In this context, they are kind of more mature, of course, but the advantage are also huge. These are how we started to study this technology. So we started with trying to explore all the domain, because I mean we understood the exclusion of any of these branch would limit a lot our possibilities, and all of them have very huge potential impact on our system. So we are studying quantum sensing, we are studying quantum computing, and also communication and time metrology. Also, if for communication, actually, we have a dedicated, let's say, another domain other than observation and navigation that is now investigating more in detail the topic. In all this domain, we work as mainly end user, because I mean we could see an impact on our product, but mainly we think that in the future some of them could become our product, but some other will be we have to let's say push for the increase of maturity of this technology, but then we will be the one purchasing this element from third parties. So our role is an end user, trying to define how this technology should be used, what are the potential, the limitations. So trying to drive the R&D together with the academia and other companies toward the direction that is of our interest. So to empower the domain observation and navigation. This is to say that we know that the TRL, so the technology readiness level of these technologies is quite different among the three branches, and this is also the reason for which our role in these three branches is kind of different. We have the quantum computing that, for the moment being, I mean, this arrow doesn't want to be precise in indicating the current TRL because it's also here is kind of various, and we could discuss the actual TRL of quantum computing in general, but it's surely lower than the quantum sensing as a branch, and the same for the optical and QKD based technologies. So this to say that on quantum computing we are defining the use case, the classical use case, defining the problems that we are willing to solve exploiting quantum computer, trying to push for the requirement, trying to push for the roadmap, but trying to externalize as much as possible to academia or the entities the actual implementation. Also, if we are building internally um, let's say a small expertise in quantum circuitry and this kind of domain. Instead, in quantum sensing, that is more mature, we are investing also within our facilities to build quantum sensor in house, and this is also something that could become a product of our company. So this is the approach is kind of different. We collaborate with universities, but we all together try to keep internal the development. And then instead for optical and QKD based technologies, for QKD is not that high the TRL, but high, ready to fly, let's say, in some sense. So we are already participating to operative mission for which our role is also different, because we act directly on the in orbit demonstrator modeling, etc. So we are three kind of a way of working based on the kind of technology, and this is what we do for each technology. What we do, we start with an evidence of potential of a technology. We in ourselves with academia we try to demonstrate the functional to have the functional verification of the technology, so to achieve TRL 3 4, so to demonstrate that it makes sense to be applied in our context, and the technology makes sense. Then we start once demonstrated the functional feature of the technology, we start to collaborate with our internal colleague from the engineering department that start to make the environmental testing, so all the qualification testing, and introduce over the technology the test that we need to demonstrate that this technology can work in space. That is something kind of complex often. And once we demonstrate that technology makes sense and can work in space at given performance, we start the proposal for a new Doni product. Doni is our department, and so we work toward products development. This is our main goal. This is what we have been done so far in the field of quantum computing. We closed 4 projects funded by different entities, but it was like a beginning start. We have 3 ongoing activities from the European Space Agency with Italian funding or by Horizon Europe that cumulatively budget around 1 million euro overall. So in this sense, we started supporting the European Space Agency in Italy, defining the roadmap for quantum computing in the field of Earth observation, and now we are starting to implement in-house some quantum circuits, and so we are proceeding this way. We have 3 ongoing activities over quantum sensing, different kind of sensors. We will see later with my colleague Mattia. Instead, Alessandro will introduce the quantum computing projects, and together on optical and photonic technologies, we have kind of a huge project in which we are currently working. Since 2022, we kicked off a laboratory in our site in Rome, and in which, for the moment being, we have been implementing a QKD-based link, both in free space and in fiber, demonstrating the deciphering of time transfer signal. And at the moment we are implementing a Rydberg atoms setup, and we also have a squid array based chip that we made with external collaboration, but this is the laboratory is currently growing, and there is a lot of things to do. In the years we grow our overall network. This doesn't want to be doesn't pretend to be a complete. Of course, probably someone is missing, so sorry for that in case. But this is to say that we are working a lot with academia and with external companies. With each one, I mean, we have a set for each of the three branches, but that's a very interesting network over Europe, and of course, we are willing to participate to any other external collaboration that is possible. So this lead me to the agenda of the upcoming speech. So this is my introduction to the quantum tech group in TAS, and then you will listen Alessandro Grilli from Thales Alenia Space introducing the quantum computing topic in the domain. Then you will have two presentations, one from Federica Torrisi on the quantum machine learning, specifically QCNN, applied to Earth observation. We have a presentation from Giorgio Panichi from the University of Milan, that is a PhD, joint PhD from University of Milan and Thales. Later on, we'll have Mattia Verducci, our colleague, that will introduce the quantum sensing topic, and Davide Sera, a PhD from joint PhD from TASI and University of Bari, explaining one of the experimental activities over Rydberg atoms. Finally, we have the conclusion. So this is what you will see in the next hours. Last slide from my side is just to say that there are many ways. We are a very young group. We are expanding. We are growing. So we are willing to have new collaboration and new people that could work with us. So if you are interested, we have many ways of collaborating. We have both staff position in our team in Rome or Turin. We have we can set co-funded industrial PhD with any kind of university in Europe. We can activate easily thesis and stage. So in case you are interested, you will be welcomed in our team. And this is to conclude my presentation. These are the contact of me, Mattia, and Alessandro, that are the three persons from Thales Alenia Space Italy. And with that, I thank you.
Thank you, Tommaso.
Okay. Can you hear me properly, Alessandro?
Yes, we can hear you.
Okay. Sorry if my webcam is not activated, but I'm having some connection issues.
No worries.
So just a brief introduction about myself. My name is Alessandro Grilli. I work with Tommaso and Mattia in Thales Alenia Space Italy as a quantum satellite solution architect. I have a background in physics, more specifically with specialization on quantum computing and deep learning. I did my bachelor in Bologna and my master at the University of Padua. So I'm sharing the screen. Okay. Can you see the presentation?
Yes.
Okay. So today I will briefly introduce you to quantum computing for space applications and give you an overview of our recent work in this emerging field. So the first question I would like to address is, why are we interested in quantum computing? So, as you may know, quantum computing promises to revolutionize several sectors, and this also includes the aerospace one. And quantum computers could solve some problems exponentially faster than any classical computers. And the benefits are not only in terms of computational time, but also on size and energy consumption, for example. However, not everything that glitters is gold. In fact, we know that quantum computers will only be useful for solving certain types of problems or some specific tasks, and they will not replace classical computers at all. Furthermore, we are currently in what is known as the noisy intermediate scale computing era, or NISC, which is characterized by medium-sized quantum processors with register have a few hundred qubits up to 1000, and also gate fidelities are still too low to enable quantum error correction. In addition to that, while we wait for hardware maturity to allow us to solve progressively more complex problems, there is also a lack of industrially relevant use cases that, as for today, we know that can be more efficiently addressed by a quantum computer. For this reason, a research group like ours aim primarily to bridge the gap between academia and industry, as Tommaso was saying before, and develop roadmaps and also identify complex problems that classical computers cannot efficiently solve, and seek for a quantum or hybrid solution that can potentially achieve better results. Also, there are two sides of the same coin. So we can aim better performance, better computational power, or we could also seek comparable performance with respect to classical computing, but using less resources. And Federica will show later an example along this direction. So to start, I will introduce some use cases. And I would like to start where our journey into the world of quantum computing began a few years ago. So within the European Space Agency project, Quantum Computing for Earth Observations, and where we set out to answer the following question. So will quantum computing bring a real advantage to Earth observation in the next 15 years? And if so, how? So basically, why quantum computing for Earth observation and space application more in general? Mainly because Earth observation is rich in computational hard problems, and this is true both in space, so on board, and also on ground. On ground, we want to solve really large-scale problems where also nowadays classical supercomputer struggle, and for this task, quantum computers will be integrated into high-performance computing platform. One example here in Italy, it's the supercomputer Leonardo held in Cineca, which is one of the most powerful supercomputer in the world. And a quantum computer will be integrated soon. And also for onboard computation, where we have limitations in terms of size, weight, and power. So we need to use less resources as possible to solve a smaller problem if compared to on-ground computation. So in some recent works of our group, one is for the solution of electromagnetic partial differential equations, or PDE, with the HHL quantum algorithms. And basically, this is also relevant for antenna optimization, for example. And the other one is the satellite emission planning problem, where we use a tensor network approach. And today we will give you an overview of satellite emission planning. So to understand why mission planning is such important problem for us, I would like to start from Earth observation satellite usage. So in fact, satellites nowadays are key scientific and operation assets because they are acquiring continuously Earth observation data. Earth observation mission do not use only one satellite, but instead constellations of many satellites. And this is because constellation provide robustness, high revisit frequency for the same region, and also flexibility to both expected and unexpected events. Satellites also support diverse type of applications, which range from weather forecasting to natural disaster management. So for these reasons, the demand for high quality Earth observation data is increasing, and this leads to the deployment of larger and larger satellite constellations. One example is the Italian IRIDE program, which is coordinated by the European Space Agency with the support of the Italian one, which basically is a hybrid constellations of over 60 radar and optical satellites, and this sort of shows the trend toward the large-scale Earth observation constellations. However, we know that planning mission for such large constellations is very computationally demanding and also requires addressing a wide range of constraints concerning, for example, the preparation time, the onboard storage limitations, and also the communication windows. And all these constraints must be considered to ensure efficient satellite deployment. So, and here it is the satellite mission planning problem, whose objective is to optimize the scheduling of satellites observations to satisfy some user requests, which want to see some specific targets, while satisfying also the mission constraints. So now there is a problem because planning mission planning this mission, the configuration time, the configuration space grows exponentially with the number of satellites involved, making exact solution infeasible at scale of future larger constellations. So the mission planning problem is also known to be a NP-hard problem, and this means that no polynomial classical algorithm is known that guarantees an optimal solution in the general case. So in this work, we address the satellite mission planning with the tensor network methods, which are designed to produce high quality suboptimal solution that maximize the constraint satisfaction while maintaining computational efficiency, rather than finding the exact optima of the cost function. Furthermore, beyond the classical simulation, we know that tensor networks share some key features with quantum computers, making them really valuable both as a bridge to quantum hardware and as benchmark for its performance. So here you can see the pipeline we adopted to solve the problem. Basically, we start from the mathematical formulation of the mission planning problem, where here we show the respective cost function to minimize. Then we adopted a Kubo formulation where the original constraints are incorporated into the objective function as penalty terms. And then we map the problem onto a Ising Hamiltonian to then perform ground state search via tensor network methods. In this case, we use the MHT library of University of Padua. In fact, we are collaborating with the University of Padua, specifically with the research group of Professor Montangero, in the context of the European project Pasquans 2. So now, for this problem, we selected a specific use case for benchmarking, which is the urban flood risk in Italian city. Basically we take the hydrogeo dataset, which is open source, and include all the Italian cities, and also featuring some relevant flood risk indicators, such as the percentage of the surface area that are in high risk of floods. And also this dataset reveals that over 2 million people are in high risk of flooding. And this is one of why this problem is so important for us. And so for the constellation taken into consideration is the Cosmos Skymed, which is made of 4 satellites, and this constellation monitors the Earth from space both by day and by night, and this is suitable for our use case of flood risk in Italian cities. So basically here we can see the table with all the orbital parameters of these constellations. And to build the mission planning instances, we firstly use ANSYS System Toolkit, which is a software used for orbital propagation. Thanks to it, it's possible to use the Cosmos Skymed constellation. We used all the orbital parameters, and we simulated the 4 satellites orbit within a selected time window of 30 days. And as targets, we selected all the Italian cities, and but it's possible to take a subset to have the right dimension of the problem you want to consider. And just by selecting the first 250 cities, it results in over 60,000 data take opportunities, which are the binary variables of the problem. So here are some results from the University of Padua. We did some tests on this dataset, this TASI dataset for both 2 tensor network ansatz, so for matrix product states and 3 tensor network, along with a benchmark with the state-of-the-art classical solver, which is Gurobi. So in this case, we can see some results, so the relative emission cost and also the emission quality, which is the percentage of constraints satisfied by a given solution, and and here we can see that the emission quality is above the 99.9%. Also, we did also an analysis of the bond dimension with the Kubo formulation of this work. This is because obviously tensor network are quantum-inspired methods, but are classical. But as said before, studying the bond dimension, it's really important to future hardware, to the deployment on real quantum hardware. Here is another results from University of Padua, which basically did a fine-tuning of the penalty constant of the mission planning instances, and also adding some transfer fields on the Hamiltonian, and this is done to escape some local minima. And we can say if the auto-tuning and the transverse fields are chosen properly, we can get the best results possible. And finally, these are some results about the convergence runtime. Now, the last simulation are still ongoing, but we know that for sizes that are over 500 of binary variables, tensor network performs better of Gurobi, but Gurobi solving the Kubo formulations. So this is good, and we can see that also with really, even in the results above, even with really small bond dimension, we can manage to get good results. So some fun next step, as I was saying, the last simulation are ongoing to analyze the actual scalability of this problem solved with tensor network methods. We will have a dedicated paper in collaboration with the University of Padua, which is coming soon. And as next step, we want to run the problem on real quantum hardware. So thanks for your attention. And now I stop the sharing, and I want to leave the stage to Federica.
Thank you, Alessandro.
Hi to everyone. I am Federica Torrisi. I am a researcher at the National Institute of Geophysics and Volcanology of Catania. And my academic background is in engineering. I completed my PhD in engineering at the University of Catania in collaboration with the INGV. And now I further specializing through a master in quantum science and technology, always at the University of Catania, and also I'm doing an internship with the Thales Alenia Space. Okay. Can you see my screen?
Yes.
Okay, perfect. So in this presentation, we will see the development of a quantum convolutional neural network applied to satellite data to detect volcanic clouds. So I want to start from the project that I've done during my PhD that I've done in collaboration with the INGV. So the main goal was the development of machine learning approaches to monitor volcanic clouds using satellite data. So what we have done was to develop a deep learning model which is able to detect volcanic clouds automatically, starting from severe images. And also, after the detection of volcanic clouds, it was developed also a machine learning approach to classify the different components of a volcanic cloud, because a volcanic cloud is mainly composed by ash and SO2. So we developed this project with severe images, and it was applied to monitor volcanic clouds from Mount Etna, but also we decided to adapt this approach to different satellite data, and we applied the same model to GOES ABI to monitor the volcanic clouds from volcanoes in Alaska. And then the main goal also was to track in near real time the volcanic clouds, so this product can be very useful also in an observatory like the one in Catania, because during an eruption, it's possible to follow in real time the evolution of a volcanic cloud. So I'm doing my internship during the master's degree in quantum science and technology in collaboration with Thales Alenia Space. And the objective of this project is the investigation of the potential of a quantum convolutional neural network to classify severe images and therefore to identify volcanic clouds. So this project is done in collaboration also with other colleagues, the NGV of Catania and Thales Alenia Space, CMCC, and also with the Department of Physics of Catania. So the idea is to use a parameterized quantum circuit used as hidden layer for a neural network, and then to evaluate the performance of this approach with a classical architecture. As satellite data source, we decide to use severe images because severe is a sensor on board a geostationary satellite, the Meteosat second generation, operated by EUMETSAT, and it has a very high temporal resolution. So it is very useful to track the evolution of volcanic cloud from its formation to its complete dispersion into the atmosphere. Moreover, it has a very good spectral resolution, one image, and in general, it has 12 spectral bands, and with a spatial resolution of 3 kilometers. So as we can see from this picture, from this animation, we have an image every 15 minutes, and therefore we can track a volcanic cloud. Specifically, we used 3 bands in the thermal infrared channel, and we decided to use these specific bands for the different absorption capabilities, because we know that in a volcanic cloud we can find ash or SO2. As absorption is the reverse of ice and water absorption, and ash particles absorb more radiation at 10 micrometer than 12 micrometer, while the opposite is for ice, which absorb more radiation at 12 micrometer than 10 micrometers. So doing the difference between these 2 thermal infrared channels, it's possible to emphasize the presence of thin volcanic ash in an image, while the channel centered at 8.7 is responsible for the absorption of SO2. So combining these 3 thermal infrared channels in this way, in the red, green, and blue channel, it's possible to obtain a severe ash RGB image, like the one in this picture, where we can recognize the volcanic cloud and also the different components. In red, presence of ash, in green, presence of SO2, and yellow, presence of both components. So this approach was already developed, and it is used to monitor the evolution of volcanic cloud. But despite the classical approaches works well and is very useful, there are some limitations. The first one is that we have a spectral similarity between volcanic ash cloud and meteorological clouds, and sometimes this can result in a high rate of false positive. Also, the complexity of high-dimensional data, because we have a massive volume of multispectral data, and also an unbalanced dataset, because we have more images with the background than images with a volcanic cloud. And so we want to try to overcome these limitations using quantum machine learning. So in general, we know that machine learning is the science of making computers learn from data how to solve problems instead of being explicitly programmed. And quantum computing describes information processing with devices based on the laws of quantum theory. So quantum machine learning combines the groundbreaking technologies between machine learning and quantum computing. And by integrating quantum algorithms into machine learning pipelines, it's possible to have some advantages like exponential computational speed up, novel data representation, and also improved generalization with less data. So while classical machine learning is already powerful, the addition of quantum computing can help us to overcome the existing limitations. So in this presentation, we will focus on the hybrid quantum convolutional neural network. So this architecture combines classical convolutional layers with quantum layers. So the classical layers handle the initial processing of the data, and while the second part is the part with the quantum circuit, in particular a parameterized circuit, which use the properties of quantum computing to perform computations and make also the final decision. And so this hybrid architecture aims to benefit from both classical layers and also quantum layers. A parameterized quantum circuit is a quantum framework where the gates have adjustable parameters, and these parameters are tuned to perform specific tasks, making them the quantum equivalent to layers in a classical neural network. One of the crucial points is the data embedding, which is the process of encoding classical information into a quantum state. So in this case, the parameterized quantum circuit is a circuit where the rotation angle for each gate are specified by the components of a classical input vector. So the output from the neural network of the previous layer can be used as input of the parameterized circuit, and therefore the measurement statistics of the quantum circuit can be collected and used as input of the next hidden layer. In general, the real amplitude circuit has been selected since it has been already demonstrated to outperform the other alternative circuits for the classification in classification of remote sensing images. And we can see the structure of this circuit in this slide. And this circuit is very good because it has different CNOT gates to entangle qubits, and this allows the model to represent a much wider range of mathematical functions, so to have a better expressibility. What we've done was to develop this quantum convolutional neural network to classify severe images in one of these four classes: volcanic clouds with SO2, volcanic clouds with ash and SO2, meteorological cloud and volcanic clouds, and the last class is weak plume. So we have a dataset with 1,200 images, severe ash RGB images, and this dataset was split in train, validation, and test. The proposed hybrid architecture was implemented by integrating a quantum circuit in the neural network, and then we conducted two distinct tests using a real amplitude circuit with 2 qubits and with 4 qubits. And to evaluate the performance of this hybrid architecture, we also compared the results with the result obtained through a classical architecture, the classical counterpart, where the quantum circuit is replaced by a fully connected layer. And then we did different tests with a different number of nodes in the fully connected layers, from 4096 nodes to 2 nodes, in order to see how the model accuracy changes when we change the number of trainable parameters. And for our training, we use as input images with a dimension 100 by 100 by 3, because we have 3 channels, the RGB, a learning rate of 10 to the minus 5, batch size which is 16, and has lost the cross entropy. And then we trained the model using 2 NVIDIA GPU. Here we can see the results using the real amplitude circuit with 2 qubits and 4 qubits. If we look at the number of trainable parameters, they are almost the same, 2.49 million in the first case and 2.51 million in the second case. But the main difference here is in the time needed to train the model, because in the first case it's just 24 minutes, while in the second is almost 7 hours. The performance are good in both cases, but the 4-qubit architecture achieved the superior performance. And here we can see just an example of severe scenes, which are classified in one of the 4 classes, which are SO2, ash and SO2, weak plume, and meteorological and volcanic clouds. And we can see an example of how the model are classifying these images with some misclassification, like this first case. And in this table, we can see the comparison between the hybrid architecture with the 2-qubit and the performance obtained using the classical counterpart of the architecture, using different numbers of nodes and therefore different numbers of trainable parameters. If we look, for example, the fully connected layer with 4096 nodes, in this case, the performance are very high, but we are training 57 million of parameters, which is a very high number compared to the 2.49 million of parameters in the case of the hybrid architecture. So we can do also a comparison if we look at the 2 architecture with the same number of trainable parameters. So in this case, we have to use a fully connected layer with just 2 nodes. And in this case, we have 2.49 million of parameters, which is the same number of trainable parameters for the hybrid architecture. But in this case, the performance are very, very low. And also, if we look at the performance, we can see that if we use a classical network with 128 nodes, we have more or less the same performance that we can obtain using an hybrid architecture. And this suggests that the quantum circuit can achieve competitive results while maintaining a significantly lower number of trainable parameters, addressing the limitations of high dimensional data complexity. And finally, we compare also the convergence time. And in this graph, we can see the number of epochs required to reach a certain threshold of accuracy. And the worst case is the case of the classical architecture with 2 nodes, where it achieves low performance and it needs more than almost 200 epochs. While in the case of the hybrid 2-qubit models, it reached good performance threshold in fewer epochs compared to the most classical counterparts. So to conclude, we have seen that we have a lot of advantages to use quantum convolutional neural network. The first is the parametric efficiency, because the hybrid QCNN can use less trainable parameters and have more or less the same results of classical models. Also, the quantum encoding and entanglement is very important, because the architecture employs efficient quantum encoding entanglement to capture complex spatial correlation within the data, and also help us to discriminate between meteorological and volcanic clouds, and therefore the high expressivity with minimal complexity. And it means that we can represent complex functions without the need for deep and dense layer. Thank you for your attention.
Thank you, Federica. Okay, I guess we closed the quantum computing part. Now we should move to the sensing, if I'm correct.
Alessandro, there is last intervention from Giorgio Panichi.
Sorry about that. Please, Giorgio.
Okay. Can you see my screen and hear me well?
Yes. Thank you, Giorgio.
Okay, so hello everyone. Thanks for joining this part of the webinar. Today I'm going to talk about quantum machine learning for Earth observation. I'm a PhD student from the University of Milan, and my PhD grant is funded in part by Thales Alenia Space Italy. So I'm a PhD in the university and with the company. My background is in engineering physics. I studied engineering physics both in my bachelor and master degree in Polytechnic of Milan. And I specialized in quantum machine learning during my master thesis and PhD. So to start off, I would like to present the lab, the Quantum Intelligence Lab. We're based in Milan under the supervision of Enrico Prati, and we are composed of 2 postdocs and 7 PhDs, and there's myself with Thales Alenia Space. We work with different companies in Italy, of course, including Thales Alenia Space, and we focus mainly on quantum computing and artificial intelligence. So, as the outlook of the presentation, to start off, I would like to do an introduction on physics-informed machine learning to tell you what's this about, and then delve deeply into quantum physics-informed neural network and their application and specific use cases. I will talk about 2 specific use cases here. One involved in the quantum readiness for Earth observation project, which has been carried with the European Space Agency from Rome, and the one in collaboration with Thales Alenia Space, which is quantum physics informed networks for orbit determination. Specifically, I would like to start to tell you about physics informed machine learning. Physics informed machine learning, it's a branch of machine learning that wants to improve machine learning methods to solve and forecast models using information given by the physical system we are dealing with. So it could be observational bias, inductive bias, or learning bias. And thanks to physics informed machine learning, we can implement into our machine learning model some symmetry constraints, conservation laws, and whatever physics tells us to help our model more in general solve our system, our problem. Physics informed machine learning started off with physics informed neural network in 2017, and it was thought as a way to solve partial differential equations. So specifically, in this example, we have the Navier-Stokes equation, and in the first representation, the first idea of physics-informed neural networks, we would have the neural network in its simplest form, a feed-forward neural network, which has as its input the domain of the implicit function in our differential equation, and as the output the field and the implicit function of the differential equation. So as you can see here, for example, in Navier-Stokes, we would have a domain composed of 3 spatial variables and a temporal one, and as the output, the components of the velocity field, pressure, and so on. So by using the feed-forward neural network to as a surrogate for the implicit function, we can make an algorithm which updates the weights in this neural network to estimate as best as possible the unknown implicit function. Thanks to this method, therefore, we're able to provide a numerical approximation to an unknown problem, which can be a partial differential equation or a chaotic time series and so on, and be able to rapidly solve this kind of complex and complex problems which do not have an analytic solution. During my master thesis, I started from this method, this physics-informed neural network, and specifically I straight away delved into quantum physics-informed neural networks, which work really similarly, of course, in the general structure, but specifically the neural network is substituted by a quantum neural network. So here, in this example, we can see that we have an encoding and measurement of the quantum circuit, and specifically we have quantum neural network layers. Then the training component is classical. So basically, in the implementation of quantum neural network, we substitute the classical neural network with its quantum counterpart. In this specific example, which we have published, and the study which we have published in Physical Review Applied, that you can see, we dive into the specific application and characterize this quantum physics-informed neural network, which can be used to solve a differential equation. On the left, you can see the solution of an ordinary differential equation, and on the right, you can see the solution of a partial differential equation. Regarding the aspect of why using this quantum physics-informed neural network compared to their counterpart, we have seen experimentally that given the same number of training parameters of both networks, the quantum counterpart proves to have a higher expressivity. This is not proven yet from a theoretical point, but a lot of experiments point us towards that direction. Nevertheless, in our work, we showed that in the worst case, they achieve a similar precision, and specifically in the case of solving partial differential equation, in this case the heat equation, we were able to achieve actually a higher precision using the quantum physics-informed neural network. So basically, this is the summary of the first part regarding quantum physics-informed neural network, and with this part I wanted to showcase to you the capability of this technology to solve differential equations. Going ahead, I will go into the first use case, which is, as I mentioned before, chaotic system prediction. So chaotic system prediction is a really important field in physics right now, because there are a lot of chaotic systems which we need to forecast, and for this specific application we want to use quantum echo-state networks. So what we basically have is a time series which is given by a chaotic system evolution, and through the feeding of a quantum reservoir, which you can see at the top center of the image, we want to predict the next step of the time series. Quantum reservoir computer echo-state, or also called in this specific case echo-state networks, also exist in a classical domain without quantum computer, but they are especially suitable in quantum computing scenario because of two main reasons. The first one is that they are easily applied and created in a quantum computer, since echo-state networks are really big neural networks with fixed weights that we do not train. We easily can create them using qubits. The only part that we train is the final layer as an extreme learning machine, and we use the final layer to train and fit the data. So this is the first reason, that that it's qubits are really easy to map. As you can see on the bottom, we have the circuit in the C figure. We have the circuit actually used for this kind of echo-state network. The second is that also noise is not a problem, as is shown in a paper also mentioned in the bottom that was published by our group. In the context of this ESA project, which depends on the suitability of quantum computers for application on Earth observation, we needed something that was ready, as the project says. Therefore, we went ahead and used the quantum reservoir for a chaotic system prediction. Specifically, we used to solve the Lorentz system, which is a system of three equations which exhibits under certain parameter condition chaotic behavior. And through this method, we were able to actually prove some good results. From this plot, you can see that we plotted this time series, which is, as mentioned before, the chaotic series of the Lorentz 63 trajectory on the right. And on the dataset, you can see that we have a classical echo-state network compared to a simulated quantum echo-state network using an EBM backend and one on the actual hardware. So these runs were both made on specifically fake Marrakesh backend and the quantum computer Marrakesh given by EBM. And we showcase that we are actually able to predict time series, even if it's now in a smaller domain. And for smaller system, we are able right now to solve this kind of chaotic system. Diving deeper into the result, we can see that the results have all good normalized error. And the correlation of each variable is really good, meaning that the trend and the memory of the echo-state network is working to predict future states. I also want to mention regarding echo-state network that it's quite an interesting approach, because we are able to do an approach of quantum machine learning with offline training. So we run the job on the hardware, which can be remote, and then we are able to actually train offline, and this is a really important part of quantum machine learning in this era, when it's harder to go back and forth to the quantum computer and its classical counterpart, the classical computer. Wrapping up the results on QR4O, we can go ahead on the last part of the presentation, which is the work we are doing with, I'm doing with Thales Alenia Space Italy. And in this work, our aim is to carry orbit determination on board of a satellite. So thanks to the quantum pin we were mentioning earlier, we want to map the observation of a space target given its measurement and determine its orbit using physics constraints and quantum neural network directly on board of the satellite. This could be enabled thanks to the capabilities of this continuous variable quantum neural network that I mentioned earlier, that since they run on photonic chips, they are actually able to be built in smaller sizes and do not need cryogenic temperatures to run. And thanks to these capabilities of this particular quantum neural network, we want to achieve an orbit determination on board of a satellite. On the right, you can see simply a dataset that we are currently using for a representation of the dataset we are currently using for this project, and on the left, the actual system we are using for the dataset. So, as I was mentioning, what we want to start from observer's measurement, go through the continuous variable quantum neural network, which proved more expressivity and proved to be able to run with low energy compared to the classical counterpart, and be able to have orbit determination directly on board. Wrapping up the whole presentation, I would like to leave you with 3 takeaway messages, which are that quantum physics-informed neural networks can outperform their classical counterparts and are actually an algorithm which can be used and it's increasing in popularity among some numerical methods to solve partial differential equations. Furthermore, that quantum echo-state networks are able to forecast chaotic systems, and as I showed before, are actually able right now with the hardware many companies give for use. And in the end, that continuous variable quantum computer can enable fast orbit determination, given the possibility to build them directly on the satellite. And with that, I thank you for your attention. You have my contact if you need, and I'm looking forward for the Q&A session afterward. Thank you very much.
Thank you, Giorgio.
Okay, so Alessandro, we can switch to the part about quantum sensors. I will share my screen. Okay, can you
yes,
confirm
perfect.
that? Okay, good. So first of all, thanks Alessandro thanks to all the organizing committee to be here, to give us this opportunity to speak about what we are doing in the quantum technologies area here in Italy, in Thales Alenia Space. My name is Mattia Verducci, and I am a physicist as background. I specialized in the Quantum Information Lab here in Rome at the University della Sapienza, from the group of Professor Fabio Sciarrino, and with work about integrated photonics and quantum simulation with integrated photonics. My career has started at the beginning. I worked in the field of data science and machine learning, but for a different business company. And then 4 years ago, I joined Thales Alenia Space, and with Tommaso, we started to understand the potentialities of quantum tech in general. And so step by step, that means project by project, we grow. And now together with Alessandro and our colleagues, we have seen Federica, Giorgio, and then Davide, we are expanding our expertise. Both us and the company strongly believes in these technologies and are strongly invested on us. So it's a pleasure, I repeat, it's a pleasure to be here to speak about what we are doing. So now I want to illustrate what we are doing about quantum devices. So let's start with a question: what is quantum sensing? What are the quantum sensors? You can think of devices that interact with a physical quantity that is interesting for us to be measured, like for example, an electric field, a magnetic field, and this quantum system react and gives us a measurement, of course, like classical ones. But quantum sensors offer great possibilities because they offer an enhanced sensitivity, meaning that we can measure very low values of the variable of interest, and they have very important property. They have an high stability. This means that they fluctuate, they drift very few in time with respect of classical sensors. There are several definitions. We can use several definitions of quantum sensors. The first one is that is the simplest one, because we are looking at the quantum object as something that has discrete energy levels. And so, by means of this quantization of the object, we are able to achieve these increased performances. And this is the most common definition of quantum sensors, the one that we will exploit in the next slides in our projects. We can also make more complex systems. For example, we can realize a collection of quantum objects in order to exploit the quantum coherence, so the wave-like nature of this ensemble of objects in order to enhance the sensitivity. And then we can also exploit the entanglement to further improve sensitivity beyond what it is classically possible. But of course, the complexity of these sensors is, as you can understand, increasing. So for space application, we are for the moment concerning the first definition. Physically speaking, what are quantum sensors? There is a huge plethora of possible technological platforms to realize quantum sensors, and the right choice depends on what you have to measure. For example, we can use neutral atoms to measure magnetic field, rotation, and also to generate time scales. In particular, these are called cold atoms, because we are speaking of systems that should be maintained at cryogenic temperature in order to make their quantum properties appearing. We can use electrically charged systems, so for example, trapped ions. We can use these that are called hot atoms, opposite to the cold ones. To measure, for example, electric field, these kind of sensors are really interesting for us, as we will see later. And then we can have systems, and these are, let me add that these are hot atoms because we can work with them at room temperature. These are gases most of the time, like for example, vapors of alkali atoms, highly excitated alkali atoms. And then we have more complex systems, like for example, condensed matter systems, like single spins or ensemble of spins. The last one category that I want to highlight here is the superconducting sensors, because we have realized we have some projects ongoing on them, and they are suited to measure, in particular, magnetic field. For those that are interested in going deeper into an introduction of quantum sensing, I have inserted here this reference to this paper from Degen et al. That is really, really good for an introductory overview on this topic. As said by Tommaso at the beginning, quantum sensors are at a middle scale of technological maturity. This scale that you can see here is a scale that is commonly used to define the maturity level of the technologies that is commonly used for space application, because I have taken it is on general, we refer on it because it's the standard from the European Space Agency. Quantum sensors are here, so between TRL 3 and 5. Most of the platforms are a bit more mature for sure than quantum computing, but less than quantum and optical communication, for example. This high TRL from 6, from 7, you can consider that is something that can fly, that can be put on a satellite that is flight proven. So what are some kind of application? Why quantum sensors are interesting for us? There are really a lot of possible applications. I have listed some of them. Of course, we are not investigated all of this because we have a limited effort, but these are really, really interested. In particular, for example, for a matter of convenience, we usually divide the quantum sensing area into 3 sub areas that are quantum sensor, properly speaking, so devices to measure something, devices to image something, so quantum imaging, and devices to generate and transfer time, so the quantum metrology. Let's dive a bit into this application. For example, we can exploit quantum objects to enhance the capability to detect RF signals, like for example for radar applications. And this is the most important topic we are currently investigating in TAS-I. We can exploit the high accuracy and high stability over long periods of time of these objects to realize quantum inertial navigation units, so that the system can be autonomous in critical context, like for example, environment in which you have not, for example, the information about your position because you are not able to receive GNSS signals, and so you have to rely entirely on your local data. And these sensors are great because they can remain stable over very long periods of time with respect to classical ones. We can use these systems for enhancing our capability for Earth observation, like for example, innovative payloads for magnetic field mapping and gravitational field mapping. We can also exploit the entanglement, so the single photon features, to enhance our Earth observation systems. So we can, for example, collect a signal in order to realize an image from a very noisy context, because with respect to classical sensors, I can be able, if I exploit the single photon measurement, I can be able to realize the image with very low signal, with very low SNR. And so this is really useful, for example, for imaging very distant targets, for increase the autonomy of space operations, in particular for the deep space mission, if you think of also our work as Thales Alenia Space. We are working on the development of a future human habitat on Mars and on the Moon. We can realize imaging through the atmosphere, through clouds, let me say, through turbulent media in order to increase the resolution, and so on. We can do a lot of things if we apply the entanglement and the single photon measurement to current classical signals. And then we have, of course, a lot of interest in going deeper into fundamental physics experimentation. For example, here in the right part of the slide, I've inserted a reference to optical clocks. Optical clocks are really important because they permit us to realize something like the LISA experiment, that is about the realization of a gravitational wave interferometer in space. Last but not least, quantum sensors can be able to detect dangerous molecules, for example, and so they are really important in the support of life in space, like for example, International Space Stations and beyond. Optical clocks are really important for us because they have a really enhanced stability with respect to classical clocks. So a clock shall be able to generate a time scale. So the main important feature of a clock is stability. The clock generates a frequency reference, and I want that this frequency reference remain constant over time. And now we are using atomic clocks that are based on microwave transitions. If we can switch, we could switch to optical clocks, meaning that we will target optical transitions in, for example, ytterbium or strontium. Then we can unlock stabilities in the order of 10 at the minus 18. This means that if you consider an age of the entire duration of the universe, the age of universe, you are drifting off less than 1 second. And of course, with this ugly accurate clock, you can enhance, you can think of next generation, for example, GNSS systems that allow you to realize positioning in the order of sub-millimeter. You can improve our Earth observation systems because you can think of relativistic geodesy, gravitational field mapping, radar interferometry, so distributed constellation of radar that should be synchronized between them, and so on. We have really a lot of interesting applications for optical clocks. I want to go fast on this part, is just to repeat that our role in Thales Alenia Space is to take this technology, assess it, and then be able to enhance its maturity, so enhance the TRL during several phases of the project up to a in-orbit demonstrator, so up to a flight model. This means that we start on general with phase A projects, and then we go to phase B1, C, and D. And on general, we need typically between 4 and 6 years to enhance the TRL, starting from a very low TRL, so around 2 or 3. What is important for us is not only the demonstration of the possibility to do these things, so to test the functionalities of these sensors, but we have, as Thales Alenia Space, we support scientific teams in order to optimize the payload, the instrument, to be resistant against the space environments, because space environment offers challenges that we have to consider, like, for example, really huge temperature gradients, vibrations, ionizing radiations, the impact of debris, and then of course we have to consider that the payload has a size in terms of volume and a mass and a power consumption that should fit on the constraints that the specific satellite platform offers. This is a slide that I have stolen from our colleague of the domain exploration and science, just to tell you what we did on the International Space Station, because in 2033 we supported an experiment and a scientific consortium to transform their payload that was something on an optical table in a lab up to something that could be put on board the International Space Station. This was an experiment about the test of the weak equivalence principle, but we are working on experiments about the gravitational field mapping with cold atoms. Just a few words about a topic that is really interesting for us in Thales Alenia Space Italy, because we are currently working a lot on it. I'm speaking about the use of quantum sensor as passive RF receivers. So RF receivers are, of course, devices that allow us to detect an incoming signals. These signals has, on general, a carrier frequencies that is between tens, hundreds of megahertz up to hundreds of gigahertz. There are really a lot of application of RF sensors in space, as you can imagine. For example, we have the space surveillance awareness. We have the so-called GNSS reflectometry, so we can exploit the signals that arrive on the Earth for the purpose of positioning. Think of navigation satellites. These satellites send to the ground signals that are collected by GNSS receivers, but a large part of these signals is reflected by the Earth surface and can be used in space to detect environmental variable of interest, like, for example, the height of the forest canopy, or, for example, the humidity, and so on. So we can exploit dedicated sensors to realize this that is called the collection of signal of opportunity. We have the radiometry, for example, in this in this image in the right part of the slide. I want to show you the SIM radiometer, that is a satellite that Thales Alenia Space Italy is prime contractor. We are building this very large antenna to collect the thermal radiation coming from the Earth surface. And of course, there are a lot of other interesting applications of RF receivers. Think, for example, to radar, imaging radar, the synthetic aperture radar, the antenna characterization in our facilities, electromagnetic compatibility tests, and so on. So these are really important, and we want to understand how, in particular, these categories of quantum sensor can help us into facing the challenges, the typical challenges of classical sensors. I want to spoiler you that we are working, we have tested the superconductors and the Rydberg atoms. We have not activities ongoing on NV Center, but we are really interested in starting this. We are ready to start these experimental activities. One sector, one area of interest is what I have called, what is called space surveillance awareness, and it's about the protection of space assets. So this is a really hot topic, because we want to be sure that our space asset, that can be the International Space Station, that could be a satellite or something else, cannot be threatened by both natural threats, like for example debris, or artificial man-made threats. In order to do this, we have to devise many sensors, for example, also passive RF sensors that should be able to detect, on general, unknown signals. By detecting these unknown signals, we can, for example, detect if an object is coming toward us or not, if it is maneuvering, if it is sending interfering signals on us. So we can understand, we can study the space environment around our asset and react, characterize this environment and react to possible threat. So for this topic, it's really important to have RF devices that can be characterized by large bandwidth, high sensitivity, low SWAP, so low size, low power consumption, because they can be used as a secondary payload, for example, and they can be able to detect direction of arrival. Classical sensors have many limitations, because if you think of an antenna, the antenna size is strictly related to the frequency of the signal I want to analyze. So if I would like to sense a large plethora of frequencies, I should have many antennas, and this is not possible on the satellite. So we are studying alternative sensor, like for example the superconductive sensor. These are a work we have done in collaboration with the Italian institution Fondazione Bruno Kessler in the context of a European founded project, a large consortium called QTest and QPilot. But I want to go on because I think that the most interesting technology in order to realize ultra-wideband compact sensor is the Rydberg atoms. I just want to tell you that conversely, what are some limitations of classical antennas? As said, large bandwidth applications require many sensors, many antennas. This sensor can be complex in terms of front end, so in terms of size and power consumption. They are sensitivity limited because of the noise coming from electronics and thermal. They need calibration, and most of the time they are made of metals that can introduce distortion of the incoming field. So we can mitigate all of these limitations by using vapors of Rydberg atoms. And Rydberg atoms will be the topic of the presentation. We will give you better insight of what we are doing on this technology. And this information will be given you by Davide in the next in the last talk. I just want to highlight here that NASA and many other institutions are working on it. For example, NASA is using Rydberg sensor as for reflectometry purposes. US Army is using is studying these systems for communication and as spectrum analyzers, and there are dedicated companies that are arising, working on this sensor for imaging. We have two ongoing activities about Rydberg atoms for RF sensing. Davide Sera will present you the activities that is ongoing with the Università degli Studi di Bari Aldo Moro, and another activity is ongoing with the European Space Agency and the Polish guys from UWRC. So before leaving the floor to Davide, I want to thank you for the attention, but in particular, I want to stress a message already passed by Tommaso, that we are strongly interested in potential collaborations. So if you are a researcher and you are interested in starting activities on these topics with us, or to define industrial thesis or PhD, please contact us. And also, if you are a student or a master graduate and you want to do with us a thesis or a PhD, contact us, of course. And also, if you are interested in working with us, we have open position. Especially, we are looking for experimental background. So also this time, contact us. Thank you again. And so I want to leave the floor to Davide.
Thank you, Mattia.
Hello everyone, I'm Davide. I'm a PhD from University of Bari, and I did my physics. I did my physics studies for both bachelor and master studies in Rome, Tor Vergata, and now I am in my second year of my PhD, and my project is on, as Mattia said. You can see my presentation. Yes. I think yes. As Mattia said, my project is on. Okay, my project is on realization of a radio frequency quantum-based radio frequency quantum sensor based on Rydberg atoms. Let me just. Okay, I can see the slide now. Okay, I am in my second year, and I want to go a little bit deep in what Rydberg atoms are. Well, Rydberg atoms are simply alkaline metal atoms, excited to a very high excited level. It starts to be called Rydberg when you go further after the principal quantum number 20. And it has a very high coupling constant, as Mattia said, and it could be vaporized in a millimeter scale glass cells. Fundamentally, in these glass cells, you have vacuum cell with inside some saturated vapor of metals. Why they are very interesting for us? Because it can be used as a calibration with physical constant of atoms, because atoms doesn't need calibration, as Mattia said, and it can use it for calibrate both magnetic and electric field. Now we are focusing on radio frequency detecting, but it can also be used for detecting magnetic field. And it has a possibility to be scaled and to be integrated in photonic chips, and possibility to be fiberized and inserted in very difficult, in very small space, like in satellites, for example. You can see here one picture from NIST in which they have a 10 millimeter cube cell fiberized, and they did radio frequency detection with it. And they can work at ambient temperature. Our test was done at 30 degrees, but they also work at 25 degrees, 20 degrees, so you don't need to heat it up or to decrease their temperature to let it work. But how it works? Fundamentally, you have here a small scheme of the cell. In cell, you need to send two different lasers. Let's call them probe laser and coupling laser. The probe laser is the laser that you also see in your detector, and you do spectroscopy of the atoms with this laser, the red one in this case. And with probe, you reach from the ground level, taking in example the rubidium, you start from the ground level 5s1/2 and reach the first excited level 5p3/2 with the probe laser. And after that, you have to reach Rydberg levels that I said is above the principal quantum number of 20. And these levels are sensible to RF source. Go a little bit deep in spectroscopy of rubidium or cesium of alkali atom in general. Here you can see a spectrum of rubidium excited to the first excited level, as I said before. So you can see here 4 dips, 2 each atomic species, because there are 2 atomic species for rubidium, rubidium-87 and rubidium-85. And if you scan in one of these dips, you can see this figure. This is just the absorption profile of the atoms, so the spectrum of rubidium. What happened when you switch on the coupling light? Atoms that are now here in the first excited level, you can see my pointer. Yeah.
Yes, we can see your mouse.
Okay, maybe it's better.
Yeah, it's better now.
Atom that is at this level with coupling laser reach Rydberg levels and stop absorbing the probe light. So what you will see after switching on the coupling light is a peak in center of absorption, because these atoms that are in these Rydberg levels are no more absorbing the probe laser. So this peak of transparency is called the electromagnetical induced transparency peak. And this is the base to see RF frequency, because now we are in Rydberg levels, and the nearest Rydberg level, for example, if we reach a Rydberg level of n, we have another Rydberg level n+1, and this level is in frequency distant. In the distance in frequency between these two levels are in gigahertz. So the distance is cover the radio frequency signals. And if you switch on the radio frequency source, you can see the peak splitting in two. And the interesting thing is that the distance of these two peaks are direct proportional to the intensity of electric field of the radio frequency signal. So you can direct link intensity of signal with splitting in a with distance of peaks in a spectroscopy. Here we have a picture and a little scheme of our setup in Thales. As you can see here, we have 2 lasers. One laser, the probe one, is split in 2 because we want to have one reference laser with no coupling laser counter-propagating it, and one signal laser that can see the radio frequency. Why these 2 different paths? Because we want to subtract from the signal path, from the signal laser, the signal from the reference one. So you can subtract from this curve with EAT and splitting the red curve alone and just isolate the peak and splitting in case of presence of RF frequency. And you can see here that from there, in real setup, comes the 2 laser for rubidium D2 line to excite at 5p3/2. We need a 780 nanometer laser in near infrared, and laser path is that one. We have some polarizer here and a Wollaston prism that is like a beam splitter, and divided the path in 2 equal beam and pass into the cell that is here. Here you can see the glass cell zoomed with laser passing inside. And okay, oh sorry. Okay. And probe laser passes through these 2 mirrors and go here in the photodetector, that is the detection here in the scheme. And these 2 channels subtract one from the other, and you can see the isolated peak. Some early result, we just started work on that, but this is simulation of how split appear in the central EAT peak in the transparency here. And this is our result, our data. We can see that split things becomes more at different power of electric field, and we can see also here a different power of the antenna. The central transparency becomes less and less, and then definitely split in two parts. You can see also here a simulation of quantity, amount of splitting based on power of signal that you send. And you can see here our data. We just can take data above minus 20 dBm because under this value of power we cannot see a splitting, but we can see a change, of course, in peaks absorption. And some works in work also go very, very, very low in power and can see very small changes in absorption of EAT, and can reach sensitivity on nano. If I remember well, yes, nanovolt on meter. Yeah. My PhD project is a collaboration between agency Thales Alenia Space and University of Bari, and we are developing two different setups, but very similar between each other. In Bari, we are using cesium atoms, and the idea is to do a very well done parameter characterization of every parameter of this setup. So powers of lasers, beam width of lasers, temperature of cell, and we want also to test different typology of cell. For example, the one that you saw in that picture is a classical reference cell from Torlab, from a commercial company. And we want to test also very small cells that will have a smaller signal because you have less atom inside. You have a smaller path of laser inside the cell itself, but would be very interesting to integrate also it in fiber and to integrate in photonic chips. In Thales Alenia Space, we are using rubidium, and the target here is to reach new sensitivity target and space use integration, of course, to satisfy also the modern day networks, the needs of the network sensitivity and metrology of modern days. This is the setup developed in Bari, and here also a picture with laser on. And as you can see, the setup is very similar. The difference is on cell. We are using this type of cell here. That is the same cell used by NIST for the fiberization. Is a 10 millimeters times 10 millimeters cube. And we are using, yes, also here balanced for detection, and here some sketch of also electronic instrument we are using. But if you have a question, I can answer on it after the presentation. And we are also trying to develop a laser written paper cell with the help of the university startup Sensato. And the idea of this cell is to write the path that you want, the sensing path and the chamber path. Inside this model, you can see a chamber here with a pill inside. This pill is a rubidium or cesium, an alkali atom pill that could be activated and could send when you need atom inside this sensing chamber. And in this model is also fiberized here. So the idea of these laser vision chips, possibility of fiberization, possibility of customize it that you prefer, of course. Here in the picture, you can see the cell lighted by the laser, Wollaston prism here, some optics, some fiber couplings, and this is the setup in Bari. Today, I for the first time was able to see an EAT peak here in Bari. I don't have any image of that. It's a very recent news, just some hour ago. But yes, we are working on it, uh, and this, what I want to show you here is what level and what radio frequency you can tune coupling using different coupling wavelength of the coupling laser for the two atoms, radium and cesium, and you can see that as also someone else says, quantum physics is not continuous; it's a discrete. And also here you can see that we can't have a channel. Let me call it a channel. But you have a lot of Ripper levels that you can reach tuning a laser of some nanometer, less than 1 nanometer here, and also less a couple of nanometer here. And you can reach all of these levels, and all of these levels can tune with different radio frequency. And those are all the spectrum of radio frequency you can tune with these wavelength tuning of coupling laser. So to conclude, here some papers from community on Ribet atoms. A lot of works comes from US and Canada, but also some European interesting works like this one from Barsav. And yeah, community is big, and a lot of people are working on it. A lot of people are studying different also setup, as you can see here from some images. Some other group are also testing all glass cell, as we in Bari want to do. And yes, that's some pills about Rydberg atoms. I hope it was interesting.
Thank you, Davide. Thanks a lot.
So I think we concluded the set of presentation. Just some conclusive remarks from my side. Just a few minutes. And I mean, I thanks all the guys for the nice presentation. I think it was kind of a hard task to shrink all these kind of technologies and works together, but somehow we did it, and we saw a number of different technologies, from computing, sensing, different kind of sensing platform, and quantum computing approach. We didn't speak about metrology or QKD, quantum communication. There are many other topics to be explored, but the time was limited. I hope that we were able somehow to give an overview of how a big tech company like our in the satellite domain operate in the R&D field, and specifically with low TRL technology, approaching with academia and working together with the universities. And I hope we have been somehow inspiring in some sense toward the space domain. And I hope that there will be some future interaction with us in some sense. And we are here to answer some questions if there are.
Thank you, Tommaso. Yes, first of all, let me also thank from our side all the speakers for the great presentation. I'm sure that you spread all the activities on a general view. I think people are interested. I saw already some comments in the chat, and I'm welcoming all the participants to ask questions if there are. And regarding the other additional topics that have been touched, I mean, not been touched, I mean, we can still organize other a separate session of these webinars, since we are running them kind of on a regular basis. So we will for sure invite you again. So meanwhile we wait, I start reading what is already in the chat. First of all, I see a lot of congratulation comments. There is Paolo Gamba with sending you applause, as well as Raul Roit, sorry for the wrong pronunciation. So he's saying that all the sessions are really informative and wonderful. I just started my career in climate risk management. As a fresh industry comer, I really find it difficult to understand such complex things as machine learning, deep learning models. I get to know so many eye-opening things from all of you. Thank you so much for this wonderful opportunity. Another round of applause from Michael Ospichef. And then we have a question from Wenbo Lee. It's kind of a long question, so I'll read it quickly for the others, but please look at it as well, so I'm not missing anything. But okay, quickly, thank you for your valuable presentation. Really appreciate the opportunity to participate in this online meeting. I'm new to quantum computing and have recently started learning about it, but I'm very interested in its application to Earth observation. I would like to ask a question. Where we combine quantum computing with deep learning, at the current stage, do we generally need to let deep learning model learn from image feature first rather than directly using quantum layers? I guess this question is for the first group of persons, so feel free to answer.
Yes, maybe Alessandro can say something, and also Federica altogether.
Yeah.
I think there are those are the two persons more involved.
Yeah, I can
Ale?
answer if you.
Yeah, well, Federica.
Yeah, I mean, I think that it depends on the architecture that we want to use and also on the goal, because in this case, we wanted to classify images. So yeah, actually, we need a classical part to extract the features and then the quantum part just to classify. So in this case, we are using a late hybrid architecture because the quantum part is at the end of this pipeline. And we are processing high-dimensional Earth observation data. But it also there are also other kind of architecture that can be used, like the early hybrid architecture, where the quantum part is at the beginning and it can be used for feature extraction. But in this case, it processes images patch by patch, and then after this quantum part, there will be a classical part for the classification. But it depends also on the goal, because in this case, we use this kind of architecture, the early hybrid architecture, when we want to extract local features.
Thank you, Federica, for the reply. So there is another question about the SAR word from Shiod. Sorry about the pronunciation. So he's already asking about any thoughts regarding quantum to be applied to in-SAR processing.
Actually, we are not working currently in SAR processing with the quantum approaches, but we would like to do it in the future. So I think that there are also available in the literature some methods to do it.
Yes, let me add that. Let me add, Ale.
And,
please
finish. No, just let me add, Ale, that yes, of course, we are not working on it, but it's of interest for us. We have started a study on the possibility to apply quantum computing to SAR processing. So it's something we want to explore in future, for sure. We know that it's very difficult due to the high number of involved, the necessary qubits.
Okay, great. So maybe we can invite the attendee to write you an email to express some more interest. Of course. Okay, I see a lot of questions popping up. So quickly, thank you from Sri Lanka, from Sandui Ratyanki. Okay, it's really going fast. Sorry, I'm losing some of them. Very insightful session. A lot of compliments from Kavana Dirajan. So no problem. I'm going to jump into the question because we are few minutes left. So from Asanabu Seda, how can you use quantum management for disaster? I think is how you can use quantum computer for disaster management. Are there any efforts in standardization of using quantum management for disaster management? And
Yeah, actually, I don't have a specific answer for sure. Sorry, Alessandro.
No, that's okay.
No, go on, Tommaso.
I was just saying, I mean, personally, I don't have any visibility on any effort for standardization, but probably, I don't know if there exists, we are not, I mean, we don't have visibility of it, and probably can be seen as, I don't know, we are not working on it, but it could be seen as an optimization problem, probably. So it could be somehow treated as an optimization problem, but as per today, it's not on our roadmap, let's say.
Okay.
Let me add that our team is studying the possibility to put calculation on board, so to enhance HPC, both with classical and quantum techniques. So we are studying quantum for future days. So in future, we would like to have quantum to enhance the computing capabilities on satellite. And this means that we can reduce the response time of our platform, and this is in the direction of disaster of search and rescue, disaster management, and so on. So in this direction, quantum could be useful, even if it will be difficult to put a quantum computing platform for the moment on board.
Yes, I agree. I mean, there could be, this problem can be seen in different ways. If you see it as an optimization problem in ground, probably to organize the management of, I mean, high risk events can be managed as an optimization problem. But as Mattia said, we are also working on board. So if we are able to notify, to sense and notify and process as quick as possible, then we can also somehow increase the quality of the information we have around and how we react to the
Sure.
disaster.
And if I can add something, even the use case I presented before, so the mission planning for Earth observation data acquisition can be in a sort of sense similar to quantum management for disaster. So they can be connected in some way.
Yes, optimizing the mission planning means enhance the disaster monitoring capabilities of our systems, also on ground.
That's correct. Yeah, indirectly, but yes, that's correct.
Okay, thanks for the informative reply. So I see that there are only other messages about thanks for the presentation. So I think we can close it here for now. I'm just want to tell you everybody that the webinar has been recorded, so and it will appear on the GRSS channels. So you can retrieve every time all the information, including the Q&A session, plus all the contacts from Thales, and yeah, I also welcome all the people that are writing that are interested about doing a PhD or an experience on this to contact all our speakers. So let me thank you again, and hope to see you next time in one of the other webinar.
Thank you again.
Thank you.
Thank you.
Bye bye. Ciao.
Thank you.
Thank you very much.